Now it's time to start learning how to interpret these results. We've already learned some of the basics of logistic regression. We learned that this is the model we're going to use. On the left-hand side, we're predicting the log odds ratio of outcomes from information on the right-hand side that are on intercept, slopes, and predictor variables. So we're no longer seeing how the predictors change the outcome directly. We're seeing how the predictors might change the odds of an outcome directly. We started the example below. We're going to predict whether a given day is an options expiration date based on two characteristics, the market volume that day and the volatility in the market that day. This is the code that we learned how to use, and we saw that we still store the model as something called fit or anything else that we want to call it, but we're going to have to use the GLM function instead of the LM function. And remember, the reason is because we need to use something that is more general and allows for the very particular violation of the normality assumption that we have. We only have a binary response variable with only zeros and ones as possible outcomes, so we can't use a standard linear regression model. You'll also see on the right-hand side of that code, we need to specify family equals binomial. This says, please use a logistic regression. And then we ask for a summary of our model. When we ask R for a summary of the model, we'll see this output. This looks a lot like what we've seen before with a linear regression model. We have the function call reminder, the coefficients section, which looks remarkably similar to what we've seen in the past, and we have model fit information, which looks a little bit different. But before we can start interpreting the coefficients, we need to do a significance test on each one. This process is going to be almost exactly the same as what we do for linear regression. R will perform a hypothesis test on each one. So first, let's refresh on what is that hypothesis test that we're doing. There will be a null hypothesis and an alternative hypothesis, and those will look exactly like they do in a linear regression. We're testing to see whether each intercept and slope is equal to 0 or not equal to 0. And effectively, we're testing to see if that coefficient is significantly contributing to the model. If it is, we'll keep it. If it's not, we'll say this coefficient is insignificant and we'll remove this from the model. And here's the test statistic. Remember that every test statistic is a ratio of signal to noise. So here's our signal, and here is our noise in this situation. And based on the maximum likelihood estimation is where the distribution of this test statistic comes from. So we can say with a large enough sample size that this test statistic is going to follow a standard normal distribution. So having a large sample size will be something we'll talk about again soon. But the signal is just the estimate of the coefficient minus 0 because that's the value we're comparing it to. The signal will be strong if beta 0 hat, the estimate for beta 0, the intercept, is far from 0. And in the denominator, the standard error of beta 0, that is a measure of how certain we are in our measurement. How wildly does this estimate vary if we change small things along the way? So if there's a little bit of noise in my estimate, is it a wild swing? Did it used to be 3 and now it's 300? Or did it used to be 3 and now it's 3.1? So that's a measure of how much the estimate changes, how robust it is against noise. So signal to noise ratio follows a normal 0-1 distribution. And this test will be very similar when we look at each slope. So if we have two predictor variables, we'll have one intercept and two slopes, and we will have to do 3 hypothesis tests. going back to the R output, we're looking specifically at the coefficients section here. We can see that there's an estimate for the intercept, an estimate for the market volume, and an estimate for the VIX close. In addition to each estimate, we'll have a standard error for each situation. So the estimate is the signal, and the standard error is the noise. The two of them together will make up our test statistic in each case. So, negative 4.89 divided by 1.64 is the test statistic. That value is negative 2.977. And when we try to find that value on a standard normal distribution, we're way down here, negative 2.977. And this value here is the probability of having something in this distribution that is as extreme or more extreme than what we found. So this is 0.002907. That's the area of the shaded region in the graph. And because that p-value is so small, that shaded area is so small, this value is so extreme, it's so far from zero for that reason. We see that there are 2 stars of significance here, which indicates that this intercept is significantly different from zero, so we will keep it in the model. We'll follow the same process for the market volume and the VIX close variables. You can see a very high z-score here, so 5.703. It has such a tiny p-value that it's very significant. And for VIX close, we have a very extreme value of negative 3.322. The p-value over here is 0.000892. It's very small, so it is significant, this coefficient. So all 3 of these values are going to be significant. They're going to be important in our model. So the next step will be learning how to write that model. If we wanted to talk about this without having the screen scratch and drawing out all of those hypothesis tests, we can look specifically at the stars on the right-hand side of the screen to see if there is 1 star, 2 stars, or 3 stars. We find that to be acceptable. These are significant coefficients in the model. Our next step will be writing the model. So how do I write a logistic regression model? I know how to write a linear regression model. It was very straightforward. This is the model output. So again, we're just going to enable drawing on the screen so we can look here. The intercept was negative 4.89, and that belongs in the model. The market volume coefficient looks really, really tiny. It's very close to zero, but we saw that it was statistically significant. So we're going to write that here. It is really, really small, but remember that market volume numbers are measured in the billions. So even though this number is very close to zero, when I multiply it by 6 billion or 10 billion, I'm going to find that its contribution is economically meaningful, even though that number looks small. And finally, I've got negative 0.397. Let's round that to 0.4, and we'll put that here in the model. And double checking my signs, I see I've got a negative here and a negative here, and that's exactly what the output said. On the left-hand side of the model, I'm not going to write the thing I'm trying to predict anymore. I'm going to write the log odds ratio, but I'm going to need to augment that because P is always going to mean the same thing. It's the probability of success. So what I'm going to do is write probability of options expiration, just so that it's very clear when I write out this model, what is P? It's a very important thing that students often miss on an exam. They will either not use the log odds ratio on the left-hand side, or they'll forget to label what P is. And I really need to know that you understand it's important to label P. So this is how I would write the model out. I would write the log odds ratio with a specific label of P, and then I would write out each coefficient multiplied by its predictor variable as needed.